Today we start one important topic, Cauchy sequence and completeness. We first start about definition of Cauchy sequence and we write this definition. A sequence xn in a matrix space is called a Cauchy sequence. Is called a Cauchy sequence if for any given epsilon greater than 0, for any given epsilon greater than 0, we can find n belongs to n. We can find n belongs to capital N such that whenever m greater than n and n greater than n, we have d of x m x n less than epsilon. Okay, now we start another problem. We just write definition of Cauchy sequence. That means two terms of this sequence distance of these two terms less than epsilon. Okay, that means one in between these two terms so many terms are belong. Okay, that means so many terms are close to each other. Okay, in this way one sequence represent this property, then we call this one is Cauchy sequence with respect to this matrix D. Okay, next, any convergent sequence in a matrix space is Cauchy. We prove this portion first. Any convergent sequence in a matrix space be Cauchy. In a matrix space be Cauchy. Then we write how we discuss about that. Any convergent sequence, we write xn converge to x, then d of xn x less than epsilon for epsilon greater than 0. Okay, now and obviously this n greater than equal to capital N. Okay, there exists n belongs to capital N. Then we show about that d of x m x n less than d of x m x plus d of x x n less than epsilon plus epsilon for all m n greater than equal to n equal to 2 epsilon. Okay, then we show about that xn be Cauchy. Now we erase this portion. Okay, and also the converse is not true. How we discuss this one? This converse is not true. That means if this one sequence is Cauchy, then this one is not convergent. 1 by n. Okay, 1 by n, this sequence is Cauchy. that means 1 by n minus 1 by n d of 1 by n 1 by m equal to this one equal to m minus n by m n less than equal to m by mn less than equal to 1 by n less than epsilon for all n greater than equal to k. Okay, where k belongs to n. Then 1 by n because c on 0 1, but 1 by n is not convergent. So we write this that means we know about that convergent implies Cauchy, but Cauchy does not imply convergent. Okay, now we reach this portion and also going to further discussions. Any Cauchy sequence in a, that means what are the Cauchy sequence in a discrete matrix space. Okay, we now talk about discrete matrix space. How discrete matrix space form? We know about that distance between these 2 points are if these 2 points are equal, then this one is 0, and if not equal, then this one is 1. Okay, now we going to these portions. Any Cauchy sequence in a discrete, any Cauchy sequence in a discrete matrix space. Okay, then we construct this sequence is, that means after certain term all terms are equal, then xn is eventually constant. If this one hold, then we talk about that d of xn xm equal to 0. Okay, less than epsilon. So xn Cauchy, that means if xn Cauchy, then xn must be eventually constant. That means after certain term all terms are equal. Okay, that means xn equal to xm for all n m greater than equal to k, where k belongs to a. Okay, so now we talk about another portion, one example. Okay, we write one example of Cauchy sequence. One important example, let x be a non-empty set, let x not equal to phi be a set. Okay, let us consider the normed linear space Bx of all bounded real valued functions on x, of all bounded real valued functions of x, functions on x under the sup norm, under the sup norm infinity. Okay, then we claim that then we claim that a sequence if n belongs to Vx is Cauchy if and only if it is uniform. Is Cauchy if and only if it is uniformly Cauchy. Okay, then what we do? Then we start about that a sequence if in x to r is uniformly Cauchy, x to r be uniformly Cauchy. Okay, if for given epsilon greater than 0, there exists n belongs to capital N such that f in x minus f in x less than epsilon for all x belongs to x, and for all m n greater than equal to n. Let us assume fn be Cauchy in. Let us assume fn be Cauchy in Bx. Then for epsilon greater than 0, then let epsilon greater than 0 be given. Since fn is Cauchy, in the normed linear space, then there exists n belongs to capital N such that norm of fm minus fn less than epsilon for m n greater than equal to n. Okay, now then we see that supremum of this less than epsilon. Okay, then fn be Cauchy in Bx and epsilon greater than 0. Fn is Cauchy in the normed linear space. Then there exists n belongs to n such that this one hold. Now, unwinding the definition of norm, we see that supremum of norm of fm x minus fn x belongs to x less than epsilon for m n greater than equal to n. Okay, now Now this implies that now this implies that this implies that for all x belongs to x, we have if in x minus if in x less than epsilon for m greater than equal to n. Thus f n is uniformly Cauchy on x. Thus f n be uniformly Cauchy on x. So we do this problem. If n is uniformly Cauchy on x, and obviously if fn is uniformly Cauchy, then norm of fn is Cauchy. Okay, not a then fn is Cauchy. Now we discuss about that any Cauchy sequence in a matrix space is bounded. Okay, we erase this our portion. Any Cauchy sequence in a matrix space be bounded. Okay, how we do this problem? Just we talk or relate x and b Cauchy. X and b Cauchy in a matrix space XD. Then Xn lies in any open ball Bxr for all n belongs. Then Xn belongs to Bxr. Okay, for all n. So what we do? Then obviously this Xn lies in Bxr. Okay, if Cauchy, then this one lies in this. So how we prove it? We know about that Cauchy means d of x m x n less than epsilon for all m n greater than equal to k. Okay, that means xm belongs to this bxnr. Okay, that means this implies that xm belongs to bxn epsilon. Okay, now Now obviously we show that this sequence is belongs to this. If we talk about that, or xn belongs to this, then this implies that xn belongs to, for infinitely many n, or for all n, b x epsilon, if we choose xm equal to x. Okay, if we choose xm equal to x, then xn belongs to this. This implies that xn lies in an open ball. That means xn lies px epsilon, this one open ball. So we show about that. That means this implies that this xn is bounded. Okay, this implies that x minus epsilon less than x plus epsilon. This implies xn be bounded. xn bounded means this one, that means say why this one is bounded. That means x1 x2 dot 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 xk, and then x plus epsilon, this one from one bound of xn. Okay, so xn bounded, so Cauchy sequence bounded. We prove these portions also. Okay, next we discuss about one proposition, which propositions are implies that any convergent sequence in xd is Cauchy and the converse is not true. We also proved previously that any convergent sequence is Cauchy and converse is not true. And also we proved same thing, xn is bounded. That means xn belongs to bxr. So we now discuss another portion. A Cauchy sequence is convergent if and only if it has a convergent subsequence. A Cauchy sequence xd be a matrix space. Let xd be a matrix space. A Cauchy sequence is convergent if and only if it has a convergent subsequence. It has a convergent subsequence. So how we prove these portions? Okay, now given xn is Cauchy sequence is convergent. Okay, we can take it as a convergent subsequence. If this one convergent, a Cauchy sequence convergent, then obviously this one also is subsequence, convergent subsequence. Now we proved converse, that means it has a convergent subsequence. Then we have to prove that this one convergent. That means Cauchy and a convergent subsequence, then sequence convergent. Okay, how we prove it? We first let xn be Cauchy. xn be Cauchy in x. xn, first we let xn be Cauchy in x. Okay, then we have to prove that xn is convergent. Okay, how we prove these portions, and also assume that assume that x n k, assume that x n k is a convergent subsequence converging to x. x n k be a convergent subsequence x n k be a convergent subsequence converging to x belongs to capital X. Okay, then we claim that xn tending to x. That means xn converges to x. How would show that? First, let epsilon greater than 0. Also, then choose n1. Such that d of xn less than epsilon by 2 for m n greater than equal to n 1. Now we start k greater than equal to k1. Okay, then obviously dx xn k less than epsilon by 2, and obviously and nk greater than equal to k, then we see that means n equal to maximum of n1 k1, then d of x in x less than equal to d of x in k plus d of x in kx less than epsilon by 2 plus epsilon by 2 equal to epsilon. So we saw about that xn is convergent. That means this one is a convergent sequence and this one is a Cauchy sequence. So we saw that here. Okay, n equal to maximum of n1 and k1. Okay, here nk greater than equal to k. Okay, then this one happen, d of x and k greater than equal to this one. So d of xn converges to x. Now we have choose one k such that k greater than n. Okay. That means here obviously k greater than n, this maximum. Okay, and this one obviously greater than n. Okay, Now we discuss about that another portion. Another portion is completeness. Okay, now definition of, we erase this portion. And Cauchy sequence convergent when it has a convergent subsequence. Okay, we show this problem, and next we show, or we discuss the first we write the definition of complete space. That means a matrix space xd, a matrix space xd is complete when this one is complete if every Cauchy sequence if every Cauchy sequence in X converges to an element in X. Now a matrix D is complete if the matrix space XD is complete. Okay, if D be complete, then XDB is complete. Now we show that 0, 1 is not complete. 0, 1 is not complete. Okay, how 0, 1 is not complete? Because we know about that xn 1 by n be Cauchy, but not convergent. So 0, 1 be not complete. Okay, next we show that any discrete matrix space is complete. Any discrete matrix space be complete. How this one happen? That means in discrete matrix space, every Cauchy sequence is eventually constant. Okay, then every Cauchy sequence is eventually constant. Then this one obviously belongs to this set. That means this Cauchy sequence is convergent to this set, this space. Then Cauchy sequence convergent to this space and convergent to a single element. So this one be complete. Now we show that R is complete. Okay, and so other problems about this completeness, but this one we discuss in next class. Today we stop here.